Hello, my name is Giancarlo Parodi, Principal Engineer at Renesas Electronics. Thank you for joining this session about transforming IoT software development with Arm TrustZone and Advanced Device Lifecycle Management. This is the agenda for today. Let's start with a short introduction of the security-related aspects and concerns. Security means something different to everyone, depending on their relationship to the item in question. If you ask someone who is using an end product, security will often mean protection of their personal data. But if you ask someone who created that product, security will probably involve protection of their development investment. End users will want protection against malware, viruses, or other unauthorized code executing on their device. OEMs want protection against overproduction and clones, as well as ensuring that the components they specify to be used on their circuit boards aren't replaced by cheaper copies. No one wants a device to be leveraged as part of a distributed denial of service attack, and software developers are quite keen to protect their software IP. There are multiple aspects to security with many different options, so it can take longer to design and implement the security aspects of the application than the main functionality of the application itself. The first step towards designing a secure product is to commit to designing in security from the very beginning. The RA family of microcontrollers provides you several layers of security-related features and tools you can build upon to support your journey to deliver a secure design. Starting from the hardware, the Secure Crypto Engine supports state-of-the-art cryptographic algorithms and integrated key and device lifecycle management. The software includes optimized drivers within the RA Flexible Software Package and plugs ideally into the Arm software and tools ecosystem. Several solutions are provided by Renesas to kickstart the development and allow easy integration of the desired features. Finally, the certifications achieved by Renesas help in building confidence and assurance of the device and software implementation correctness, and reduce the effort and cost for your end product certification. Let's look now at some specifics of the new RA family devices. This slide summarizes the value proposition of the RA family as a whole. Today, we introduce the expansion of the RA family of 32-bit microcontrollers in the RA4 and RA6 series with state-of-the-art Cortex M33 cores implementing the latest Arm v8m architecture. The new devices include excellent choices of peripherals for human-machine and machine-to-machine communication, memory technology, and system-related architectural solutions. With 200 MHz operating frequency, they deliver high performance with best-in-class active power consumption. The high integration level allows rich connectivity and up to 2 MB of integrated code flash with dual bank architecture for easy and safe upgrades in the field. The RA family is an ideal foundation to implement connected applications, well supported by several flexible software solutions and tools. As a fundamental pillar of the RA family value, a solid security foundation is designed in as part of the device family definition. Thanks to such advanced features, the end user can benefit from a functionality comparable to a secure element-based solution, but fully integrated with better performance, unlimited secure key storage, key management features, and lower bill of material cost. The RA mainstream family is a general-purpose microcontroller for IoT and many more markets and applications. RA is perfect for building automation, metering, and home appliances with a wide and scalable lineup, rich analog features, and endless communication options. The family is also an excellent fit for industrial automation applications, thanks to the product longevity program for 15 years plus availability, support of 105-degree operational temperature, and several safety-related features including ECC RAM memory. Security is a must in the IoT world, and the integrated crypto engine combined with the Arm TrustZone technology lifts end products to highest security levels with less effort. The RA family is also rich of connectivity and has large on-chip RAM to accommodate any communication stacks. Now let's look at the security-related features of the RA family. As mentioned, one of the strong value propositions of the Renesas RA family are the built-in security features. The heart of the RA family security capabilities is the Secure Crypto Engine, an isolated subsystem embedded within the MCU. The Secure Crypto Engine is protected by an access management circuit, which shields and protects the hardware resources by monitoring the bus interface operations and shutting down the crypto engine in the event of an illegal external access attempt. It includes hardware accelerators for both symmetric and asymmetric cryptographic algorithms, as well as various hashes and message authentication codes. It supports AES up to 256-bit key sizes, with all major operation modes supported, including Galois counter mode. It supports RSA up to 4 kilobit keys, ECC up to 512 bits, and secure hash functions up to 256 bits size. These hardware accelerators reduce the execution time by boosting the algorithm performance and dramatically reduce the operational power consumption. The Secure Crypto Engine also contains a true random number generator, which is NIST compliant and certified. Included within the Secure Crypto Engine are a hardware root key, which is used for installing customer keys, and a hardware unique key, which is used for the secure storage functionality, as we shall see later. Also, there is a dedicated logic built in for all key management operations. TrustZone is an ARM technology which allows hardware separation of the application software and its associated resources into a secure and non-secure processing environment. To allow communication between the two, the secure world defines non-secure callable APIs, which get mapped into a table of trampoline functions. Such functions are used to switch the processor into secure mode efficiently without requiring interrupts, and provide services to the non-secure world. Essentially, the non-secure callable APIs grant access to secure resources and features in a controlled fashion defined by the secure environment. At the system level, there is more to the processor's view of the secure and non-secure partitioning. It is necessary to isolate and control resource access by other independent bus masters, like direct memory access engines and the like. Since these can be programmed to autonomously transfer data to and from memory and interact with peripherals, they are potentially capable of bypassing the CPU-defined secure partitioning. And similarly, internal peripherals and their input and output terminals must be protected by non-authorized software access. Renesas has designed several security attributes and filters within the internal interconnections of the device to protect from such threats. To prevent non-authorized, malicious, or accidental changes to the non-volatile memory contents holding the application code, each individual block of flash memory can be protected from erasure and reprogramming. In production, it is also possible to make such protection permanent, meaning non-reversible. In this sense, those blocks of flash behave like one-time programmable memory. This is the typical use case for storing a bootloader code or other root of trust assets like permanent keys or device certificates. In many cases, it is necessary to monitor the environment and detect unexpected or exceptional events. This might be required by regulations or simply desirable for protecting the equipment from tampering. An example could be detecting the opening of the equipment's enclosure. The RA family includes a functionality to detect and log the timestamp of such event automatically and in a secure manner, as long as the battery supply lasts. In addition to what was mentioned so far, each MCU includes a 128-bit factory programmed unique serial number. Besides from the ARM-defined memory protection unit, there is a Renesas-designed bus master memory protection unit for the internal bus interconnection. This is useful to enhance the system reliability against DMA transfer errors, for example. The configuration for secure and non-secure memory boundaries is applied via a user-programmable implementation-defined attribution unit, or IDAU. The IDAU settings are applied right after reset, and can be easily configured for any type of internal memory included in the microcontroller. Peripherals and input-output pins are provided with software programmable security attributes to isolate and partition the associated resources within the secure and non-secure domains. An implemented protection from non-intrusive, simple and differential power analysis attacks against the secure crypto engine operation is being verified and in progress. To further provide upgrade options in the field, in addition to the dual bank architecture, the devices can perform a swap of either some portion of the upper flash memory, which can be used for application code updates, or the initial blocks of program flash, which is ideal for updating bootstrap code. In a glance, there are several options for the user to select the best fitting architecture and update strategy for the application software. The debugging and programming interfaces can be shut down or protected by means of a challenge response authentication procedure using cryptographic keys. Such functionality is reliably linked to the device lifecycle state, as we will see in a few moments. Managing assets securely has never been so easy thanks to a hardware unique key included in the device, which combined with the key wrapping support of the secure crypto engine enables unlimited secure storage and secure factory programming. At the same time, for applications concerned with legacy system support, plain text key usage is also possible, providing maximal compatibility to existing ecosystems. Talking about certifications, the Cryptographic Algorithm Verification Program provides validation testing of approved algorithms and their individual components. Those that successfully pass the tests are added to a published validation list. This certification guarantees functional correctness and interoperability, has a worldwide recognition, and is required or desired by various industry segments. Therefore, Renesas is committed to validate the cryptographic functionality included in its secure crypto engine according to the CAVP program. Both RSA and ECC Crypto are currently in the process of obtaining CAVP certification. AES, SHA, and the DRBG portion of the True Random Number Generator are all already CAVP certified. Arm has published a platform security architecture specification including a security framework that guides implementers through 4 stages: analyze, architect, implement, and certify. PSA certified is intended to give device manufacturers confidence that their products follow good security practices as being outlined by these specifications. A compliant software reference implementation called Trusted Firmware M is openly available, and this is an ideal baseline for any manufacturer using Arm technology to harmonize and deliver the features defined in the PSA specification. Renesas recognizes the importance of the PSA initiative, and therefore is committed to certify its product according to the PSA specification requirements, including the Trusted Firmware platform. Successful certification of Level 1 compliance has been already achieved, and the successive levels are being finalized and will be completed very soon. Let's dive now a bit more into the embedded features of the security solution and see how these are used to protect valuable customer assets. The most critical aspect of any encryption or authentication scheme is the key storage. The RA Family MCUs, including the latest crypto engine, feature 2 new types of keys. The first is the hardware unique key, a 256-bit random key that is pre-programmed in the Renesas factory. This key is stored in unmapped flash, making it inaccessible to application code. It is further protected by being stored not in plain text, but rather further wrapped by a hardware root key included within the secure crypto engine itself. The Advanced Device Lifecycle Management is another new feature for the RA Family MCUs. At the MCU level, the DLM is designed to protect Renesas customers' IP during the lifetime of the product. DLM state transition regression can be enabled via cryptographic authentication. The keys required for the authentication procedures are also stored wrapped by the MCU's hardware unique key and are located in unmapped flash. Key wrapping can be applied to keys for secure key storage with a built-in integrity and authenticity check. If we use the MCU hardware unique key to wrap our stored keys, we add another protection feature, clone protection. If the wrapped key is transmitted or copied to another MCU, that MCU's hardware unique key will not be able to unwrap or decrypt the information, maintaining the security of the key. We can see that MCU-unique key wrapping provides many benefits. The encryption aspect provides confidentiality of the key. Wrapping adds integrity, with special wrapping techniques enhancing that to provide authenticity. Finally, wrapping with the MCU hardware unique key adds clone protection. Let's look now at the key installation process as it happens on the MCU. For secure key installation, Renesas provides a key wrap service available at no charge, which leverages the MCU hardware root key. To use the key wrap service, a user must create an install key. This key is used only to install other user keys, and its lifetime ends after the other user keys are installed. To use the service, the user sends the install key to the Renesas key wrap service, which is hosted on a secure web service and utilizes PGP encryption for all data transfers. The key wrap service then returns a hardware root key wrapped install key. When the user sends this wrapped key to the MCU is able to unwrap it and use it within the secure crypto engine. This enables the user to encrypt his user key with the install key and send his key in encrypted form to the MCU. The MCU can then re-encrypt the user key inside the secure crypto engine by wrapping it with the MCU hardware unique key. This mechanism enables secure key installation with no plain text keys transferred or exposed, even on the MCU itself. Renesas key wrapping provides many benefits. For example, MCU wrapped keys can be stored in non-secure memory, resulting in practically unlimited key storage capability plus clone protection, since even if the entire MCU contents are copied into another MCU, the wrapped keys cannot be unwrapped, exposed, or utilized. The RA family also offers support for many use cases for secure key storage. The Renesas key wrap service enables secure installation with no plaintext key exposure, as we have seen. This eliminates the need to use a hardware security module in the final production line, since all material exchange between programmer and MCU is encrypted and not exposed during the process. Plaintext key installation is supported for compatibility with legacy systems or key installation in a secure manufacturing environment. The SCE also provides the capability to generate keys for most of the supported cryptographic algorithms, including RSA and ECC, exporting the private part of the keys in wrapped format. Device Lifecycle Management is designed to provide IP protection during the entire product lifecycle, from development to deployment to potential end product failure analysis. The RA family MCUs offer new, flexible lifecycle models. This slide summarizes the advanced device lifecycle management features. They are able to enable new business models whilst providing strong IP protection and failure analysis capabilities. RA family MCUs support 3 DLM state keys. Once the secure product developer has completed development, he programs the secure portion of the application and provisions 2 keys, one that can be used for eventual product return authorization, and one that allows an authenticated regression to the secure development state. Then the MCU is transitioned to the non-secure development phase. When the non-secure product developer has completed the entire application development, he programs the non-secure portion of the application and provisions a key that allows an authenticated regression, this time to the non-secure development state. The MCU DLM state then is transitioned to the deployed state, and the final product can be delivered to the end user with IP protection enabled. If at some point the end product user returns the product to the developer and the developer wishes to debug the application, he can use the appropriate DLM state key to regress the state and re-enable the debug interface. In the unlikely case the developer believes there is a problem with the MCU itself, he can benefit from the built-in RMA procedure support. Alternatively, the developer can choose to deliver his end product with the debug and programming interface completely locked. Now I will hand over to David, which will introduce you some tool-related aspects.
Thank you, Giancarlo. Hi, my name's David Noverraz. I am Principal Engineer at Renesas Electronics and responsible for the Arm MCU development tools. During this session, I'd like to introduce you to a few security issues that development engineers face when preparing a secure embedded design and how the RA devices and tooling address these. Firstly, setting the partitioning between the secure and the non-secure code and RAM regions is a critical design decision. Setting them too large will potentially waste limited MCU resources, but more importantly, enlarge the attack surface of the embedded application. Once the partitions have been defined, it is also important to ensure that they are protected from malicious attack during, for example, over-the-air firmware updates. Failing to manage these aspects potentially undermines the power of TrustZone in embedded designs. So let's take a look and see how Renesas have addressed these concerns. In many designs, the register pairs associated with security partitions are set during the initial project definition phase. Hopefully these are reviewed during the development phase before end production. However, are they always reviewed? The figure on the right shows a typical toolchain development flow where source code is parsed by the compiler and combined with the assembler and a library code by the linker that then generates the end application image. In parallel to that, the TrustZone boundary pairs are considered and at some stage merged to the application. Tools such as SCES Zone help with these definitions, but just how large should those partitions be? Or more importantly, how small can that secure region be to ensure the attack surface is as small as possible? To enable the development engineer to focus on the application, it makes perfect sense to automate the task of setting up these partitions. Within the C or C++ toolchain, the linker is well aware of how much secure code and data is being produced by the application, so this is where we need to be looking for a solution. Within the Renesas RA tooling, we devised a method to extract the partition details automatically to large enough but no larger than needed for the end application. The figure on the right shows how the TrustZone partition pairs are extracted from the end application image during the normal build process. And this, as I've said previously, has been developed for the Arm AC6 compilers as well as GNU and the IAR system compilers. The extracted information is then stored in SCES Zone compatible files so it can be reviewed later if needed. These partition values are then programmed into the MCU during each and every debug session to ensure that they are always in sync with the development and debug process. Okay, using the procedure that I just outlined, we have established a set of partition register values. So how could we protect them in the end application as they are potentially still at risk from over-the-air updates or malicious attack? Firstly, in the RA Cortex M33 MCUs, we have chosen to implement the Implementation Defined Arbitration Unit, or IDAU, and place this behind the immutable boot sequence of the device. This means a physical connection to the MCU is necessary to place it into boot mode before we can alter or update the IDAU register pairs. Having said that, hardware could be devised to do this remotely. However, this would have to be a conscious design decision within the team, and shouldn't really be taken lightly. This then protects the partition values from malicious or accidental corruption during over-the-air updates, for example. The entire process has been automated as part of the debugger connection using the Sega J-Link or the Renesas E2 range of debuggers. Other solutions are currently under investigation. So having developed the register pairs, we now want to actually be able to program them into the device. So how does that process actually work? So in normal mode, the immutable boot code starts immediately after the MCU is powered up. It initializes the device to a known valid state with stabilized clocks, etc. And once complete, the boot code then branches to the MCU reset vector and the application code starts as normal. And this is represented by the figure at the top of the slide. However, in boot mode, we go through a defined sequence of pin setup during power up. The immutable boot code then starts running and will perform a number of functions before branching to the application reset vector. So first of all, we will sit waiting for a valid data packet to be sent to the device through a UART channel or USB. If secure keys have been applied to the DLM, as Giancarlo mentioned, authentication checks are then made as necessary. Keys are exchanged and access is granted or not as necessary. Provided we pass the authentication checks, the boot code then accepts new partition register pairs and possibly application code as necessary. After flashing these partition pairs and application code into the device, it can be then placed back into normal mode and resume from the reset vector as previously mentioned. Following this method, the partition pairs and the target application are protected behind the immutable boot code and encrypted authentication key management, ensuring that it cannot be altered either maliciously or accidentally in the field. To ensure a smooth development process, the complete procedure has been automated during debug connection, as I've mentioned previously. So just to summarize these particular aspects, building on the excellent foundation of TrustZone, the enhancements that we've built into the RA Cortex M33 devices offer enhanced security and the confidence for development engineers to focus on their end application. That concludes the presentation. Thank you very much for your time. If you have any comments or questions, please feel free to contact Giancarlo or myself as necessary. Thank you very much.